Okay, in this third video, I'm going to look at the example that Matthew has put in his by looking at recursion. Recursion is a very, very complex and important concept. Complex, I say, because you can get confused with it. And in order to help us get our head around it, let's have a look at how a factorial works. So if I pass a factorial, so you often see this in mathematics written like that, or we might write that format. And the basic logic is, if I have factorial of 3 factorial, that actually evaluates to 3 times 2 times 1. If I have factorial 4, that evaluates to 4 times 3 times 2 times 1. If I have factorial 5, you'll see it's 5 times 4 times 3 times 2 times 1. Now what's interesting is that actually if you look at 5 factorial, it is essentially 5 times 4 factorial. And 4 factorial is essentially 4 times 3 factorial. And so you start noticing this relationship as you move up with increasing numbers. And you can see that there is a pattern here in the way that factorials are constructed. So let's look at how we would define that in terms of recursive function. Now I just want to complete this picture. If I have 2 factorial, it's 2 times 1. If I have 1 factorial, it is essentially 1. And if I have 0 factorial, you will find that with 0 factorial, it will also give me 1. So we end up with a very, very interesting relationship. If I want to evaluate 5 factorial, essentially, I want to evaluate 4 factorial times 3 factorial and so on. I can use this pattern of numbers to help me see how to construct recursively by using the same function again and again. That's what we'll attempt to do. So let's go to our code window here and define a factorial function. We're going to call it factorial. We're only going to deal with integers, pass in an integer and receive an integer. So what's our basic factorial going to be? Well, we need to set some conditions, okay? And under certain conditions, things will work. But first of all, I'm going to, if n is greater than 0, this will evaluate through to n times factorial n minus 1. Let's just have a look at what that says. If it's greater than 0, so it could be 3, it could be 4, it could be 5, it means that you're multiplying the number times the previous factorial. What does that mean? Well, look, if we look at these examples here, as we said, so if you're trying to work the factorial of 5 factorial, that's 5 times 4 factorial. If that's n factorial, that's n times n minus 1 factorial. That's the relationship we are modeling here in this particular statement there. So if n is greater than 0, we have to use that particular. We use another guard because if n is actually equal to 0, we just evaluate it to 1. Now, will that work? What's the issue? Now, you might have noticed I didn't split up my parameter type statement versus the actual statement to do with that. I've just corrected that. So those who were following this and wondered why it wasn't quite right. So there's my function, pass it a number n. If n is greater than 0, I evaluate n times n minus 1 factorial. If n is equal to 0, it evaluates to 1. Now, the only issue here is that if you end up having negative numbers, as Matthew points out, so you really actually, you know, say you pass in factorial, let's test it out, right? So I've got factorial 3 and it evaluates to 6. So that's 3 times 2 times 1. Sounds reasonable. Let's do 4. That should be 4 times factorial, which is 24. But what happens if I do a negative number? Negative 4. you'll notice straight away there's an error. There's no way of evaluating the factorial with this negative. So we need a further guard to cover the condition, an otherwise condition. So so we've got n is greater than 0, n is 0, or otherwise, we just simply pop up a message. Or we could just put 0, just to stop it from throwing a wobbly, or pop a message up, error. Yeah, I mean, technically you don't do the factorial of negative numbers. So really, actually, what you want is, we'll ignore it for the time being. You might actually want to think about what that might mean, but we're not worried about that. Technically and strictly, we need a way of stopping it from crashing. So we have a very simple recursive function. We define the function. They're the parameter types and result types. We define it with these two guards. If it's greater than 0, we evaluate that statement. Notice that when we evaluate that statement, we will reevaluate the factorial function with n-1. So it will recursively pass n-1 in, check that condition, and go on in that particular way. To confirm, let's run it, and it runs to 3. In this environment, it's very happy not to go into the negatives, because as you remove 1, you're clearly going to move into negatives. And so this is why Matthew has put into his notes that you need to cover that condition. In this particular instance, it's happy not to do it. Let's have another look. Let's have a look at another one, and we're looking at a concept here about primitive versus general recursion, but let's work the example through. To multiply two numbers, you can follow a recursive process of addition. Now, we give that often as a nice problem for students to work out. So if I pass it two parameters, under the condition that n is equal to 0, we will actually evaluate to 0. Under the condition that n is greater than 0, we evaluate m plus, and then we recursively call multiply, and the first parameter is going to be n minus 1, and the second parameter is m. So once you get used to the syntax, there's the definition of types. They're the two parameters. Under this condition, we evaluate to 0. Under this condition, we take the m value and we recursively call multiply on n minus 1 and m. You notice it will recursively add up all the values. So let's just test it out. So we've got multiply 2 and 3. 6, let's say 2 and 6, 12. So it's a multiply based entirely on a recursive call of adding numbers with its recursively dropped n value. Let's have a look at the very last example Matthew has. It's got a divide function. So if we have a divide function, you take 53 and you divide it by 10, the output will give you 5. 10 times 5 is 53. Obviously it's fractional, but we're using integers here. If you have 43 and 10, we get 4. Now what's interesting is if you try to divide 3 by 10, you end up with 0 because we're dealing with whole numbers. So how do we actually model this particular type of divide? And I'd like you to think about what's going on in terms of the general recursion. So let's pop it into here. We're going to define our types, and as I said before, it's going to be integers, integers, and integers, and the logic is going to go like this. So we get our divide, we've got our two parameters. First guard, first set of conditions is if n is less than m, we simply evaluate to 0. So this is the case where 3 is divided by 10. Otherwise, we Oops, otherwise we are recursively going to evaluate 1 plus recursively calling divide, and the first parameter is going to be n minus m, and the second parameter m. It's worth you checking that out, so let's test this out here. So I'll call divide, let's take 53, 10. 5, as we said, and we noticed before, we take 43 and 10. Let's take 4 and 10, evaluates to 0. So this is another way of constructing a recursive function.